In Hadoop, we use mutual information, which is very handy because we can actually do it in a single pass in Hadoop. So we can just make one pass through all the data, which it's quite large, and we can do it kind of in a distributed fashion. In Hadoop you distribute it to all the different mappers. So we can go through the entire data set in one pass and calculate and figure out which are the most likely features which features are most indicative of maliciousness or most indicative of benignness. Then we can take say 1,000 features, like we can add additional complications to it. But suppose we just take 1,000 features and we use those to build a machine learning model using kind of logistic regression or linear SVMs. And then we can share that model with the firewall and say, this is your model, and here's...
The model is effectively that table? Or?
For logistic regression, the model is this table.
Okay.
I said there were two algorithms that we support. So for some types of file, for example, JavaScript, there's just an enormous number of them that come through the firewall, and so it doesn't make sense to try to. We need to minimize the amount of memory used, and so that's why we use logistic regression. For other types of files, for example, PE files, that's like executables and DLLs, we're going to have to use a nonlinear algorithm because in practice, I think part of it is that the malware authors are better at disguising executable files and PE files than they are at, for example, disguising JavaScript or Flash or stuff like that. They're not as advanced in that area. So for PE files, we need to use a nonlinear method. We're using gradient boosted trees, with which you can use common algorithms like XGBoost or gradient boosted decision trees. So for those, they have a different. They still use the n-grams, but instead of using this table here, the classifier is more of the sort of this. You have a bunch of very small trees, and each tree is like a random forest tree. It says like is a number of AB, the n-gram AB less than 3, and this one says is a number of BC greater than 4, and then maybe this tree says, okay, add 0.3. So it's a series of these trees. So there's say times 1,000. So we have 1,000 such trees. 1,000's or maybe 5,000 or something like that. This is a general. This algorithm is we did not at all invent logistic regression or this algorithm, but this is an algorithm that's a nonlinear algorithm that's in practice been quite successful for PE files. So for PE files, we're willing to pay more costs in terms of memory in order to get a more accurate algorithm. One of the tricks here is that the problem with a nonlinear algorithm is you need to be able to measure nonlinear effects between two different variables, which means that you have to actually keep track of all the variables. Here we didn't have to keep track of all the variables; we could just accumulate them to a single float. But here we're going to have to actually keep feature vector. So we're going to keep a feature vector for each of our 1,000 features. For example, how many times that feature occurred. How many times did AB occur? How many times did AC occur? And so forth. I'll note that while most of our features, say 950 of the 1,000 features, are n-gram features, we also have some features that are written by other experts on PE files but they have to be things that can be kind of calculated in this way as things are going by. So it's not just engrams.
Can you give an example of one of those?
The PE file have its certain structure. So probably like how many sections in that files is one of the features.
Okay,
so
which would require you to look at kind of each packet incrementally to come up with a count?
A lot of them can be determined just by looking at one particular section, which is the header section of the PE. And you can look at, it'll have information about the PE.
Okay.
So every PE has its header section.
But that's more, I'll say, kind of standard static analysis.
Standard static analysis, yeah.
Okay.
One interesting thing about that features, is that one of the features says how long the PE is going to be. Mm-hmm. And we use that as a proxy for how long we think it's going to be. Now, it's not a requirement that the PE is that long. It could be longer than that. It could even be shorter than that, although that'd be very strange. So what we do is we assume that is the end, where the end of the file is, and we cut off. We run this algorithm up to that point because we have to kind of pick a place to stop. Mm-hmm. If there's more after that, which is much more prevalent in malicious files than benign files, we note that there's more, but we don't analyze it. This is so if we're running the file in Wildfire, of course we get the whole file. We deal about this is called the overlay. So this overlay section of the code is the section after the PE. It says the code is this long. So we know about the presence of the overlay, but we don't know what's in the overlay when we're doing this analysis. And of course that means that here when we capture the engrams for the file, we'll capture everything up to the overlay and then everything after the overlay. You can always, if you want to do analysis on the full engrams, you can always add them together, minus some end of thing effects that's pretty close to the actual numbers. But as far as the system goes, we're only going to use the things before the overlay because, and that lowers our accuracy slightly, but not that much. Anyways, I was describing the gradient boosted decision trees, or just boosted trees. So each of these is going to come up. Each of these trees is going to come up with a number, and basically the algorithm is we run the sample through each tree, and each tree comes up with a value, and then we add the 1,000 trees together, and that will be the score. And then again, we compare that to some constant. And if it's greater than a constant, then it's malicious.
And I'm sorry, so for each of these trees, you've got an array where you're storing the values. So do you have 1,000 of those, or maybe just speak to that again?
Right. So there's just as over here we had one piece which has the representation of our model, mm-hmm. and one piece which is the memory that was actually used per session.
File. Yeah.
We'll have a similar thing over here. So the trees themselves will be
are fixed, I guess.
Are fixed.
Okay.
Yeah.
Makes sense.
Yeah, for until we get a new model.
Right.
But they're fixed.
So that can be stored on disk and loaded into RAM or whatever it is, but that's actually quite small.
Right. They can be stored in what's called shared memory, which then can be accessed by multiple sessions that are running, because there's huge number of sessions.
Okay.
So the per session cost, though, is we have to store the feature vector. Because we're looking at interactions between AB and AC, mm-hmm. between these two numbers, we need to store each of the features. We need to count up how many ABs there are and how many ACs there are, and
because you can't just increment.
You can't just increment because we're looking for nonlinear effects between the two of them. So
each session would have one of those.
Yeah, each session would have one of those. Although we can cut the memory down quite. I'm getting more into details, but we can cut the memory down quite a bit, in that we can assume that the numbers are. Let's say we're going to only use 1 byte here. So a normal machine learning algorithm, you would use floats for every single feature because you have plenty of space. Yeah, but here we can cut it down to 1 byte. So that's a number between 0 and 255. Right, 256 possible combinations. So each one can be a number between 0 and 255. So what we can do is we can just cap if we're counting numbers, we can just cap them at